Okay, so now we're going to get into a discussion of solutions, and later on we'll talk about solution stoichiometry. All right, so what do we mean by the term solution? Well, we actually met solutions before. If you recall, I think in chapter 2, we talked about the fact that we have two types of mixtures that can exist: homogeneous mixtures and heterogeneous mixtures. And remember, we said that homogeneous mixtures are basically mixtures that are uniform throughout. Well, another alternative term for homogeneous mixtures is solutions, right? So any homogeneous mixture of two or more substances, we call that a solution. So for example, if you add sugar to water, you stir it, all the sugar dissolves, that's a solution. All right? And as we're going to say here, in any solution, there are two parts. You have the solute and you have the solvent. The solute is a substance being dissolved, and the solvent is a substance that is doing the dissolving. All right? Now, when it comes to different types of solutions, there are some substances that are always considered to be solutes. For example, if you have a solid dissolved in a liquid, then the solid would be the solute and the liquid would be the solvent, right? If you have a gas dissolved in a liquid, then the gas would be the solute and the liquid would be the solvent. However, if you have, for example, two liquids dissolving each other, then the one in greater amount would be considered to be the solvent, and the other one in lesser amount would be the solute. So I just thought I should share that with you so that you get a picture of what we're talking about here when it comes to these two terms. Now, when we're talking about the concentration of a solution, basically we're talking about the amount of solute in a given quantity of either solution or solvent. So a solution that is very concentrated has a relatively high or large amount of solute compared to the amount of solute or solvent that is present. But in the case of a dilute solution, the amount of solvent, or I should say solute, is small compared to the amount of solvent or solution. All right. So these are terms that we use, but they're not really quantitative. All right. In fact, these are relatively terms. So you can have one solution which is being more concentrated than another solution, or one solution being more dilute compared to the other solution. All right. So for more quantitative examination of solution, there are several ways of expressing concentrations. The one that we'll be focused on here in this chapter is molarity, which by definition is the moles of solute divided by liters of solution. All right. So in terms of units, what you'll find is that because the unit of moles is moles, of course, and the unit of volume in this case is liters, then the units of molarity can be expressed as moles per liter, which is also the same thing as uppercase M. So whenever you see uppercase M representing the unit of molarity, it's the same thing as moles per liter. All right? So for example, a solution that is 0.35 M sucrose contains 0.35 moles of sucrose in every liter of solution. All right? And very important, and we're going to talk about this in more detail later on. Keep in mind that when it comes to the molarity, the liters part of the equation here, which is the denominator, refers to the liters of solution and not the liters of solvent. And that will become important in an example that we're going to see shortly. All right? Okay, so that's just some introductory comments about the whole concept behind molar concentration. So here's the example I'm thinking of right now. In this example, and this is typically what we do in the lab and basically labs all over when it comes to making solutions of a specific concentration. So in this case, we're preparing a solution of 0.010000 M potassium permanganate. All right, so that's the molarity of the solution that we're trying to make. So the first thing we need to do is figure out how much solute we're going to need and what volume of solution that we're going to use. Now, from the look of things, we're using a volumetric flask here. I don't know how many of you are familiar with this piece of glassware, but basically it's a piece of glassware that is accurately made such that there's a mark on the stem right here which represents a particular volume. So if you add liquid to this piece of glassware and the meniscus gets up to that mark, then basically that would be the volume of the liquid as represented by the number here. Now in this case, it's 1,000 mils or 1 liter, so this would be a 1 liter flask. So if you add a liquid up to this mark right here, then you have accurately 1 liter of liquid in it. Okay, so as we said before, we're making this solution here of this molarity, 0.01000 m potassium permanganate. So what that means is that for 1 liter of solution that we're trying to make, you need to basically have dissolved in it 0.01000 m or moles of potassium permanganate, which means that we have to figure out the mass equivalent to this moles. So of course, we know how to do that. We basically take the moles, which is the 0.0100, and we multiply by the molar mass, and that will give us the mass in grams of the potassium permanganate. So as you can see in this picture, this person is weighing, whoever this person is weighing 1.580 grams of potassium permanganate, and then that person adds it to the flask. And typically what we do is that we have enough water in the flask, which should be about a half to a third full of the flask right here in terms of the water, right? So we don't put 1 liter of water in the flask quite yet. What we do next is that we make sure that the potassium permanganate dissolves in the water. So you have to stopper it, and then you have to shake it up, agitate it a bit, so that the solution is homogeneous. And then you add water more slowly until you get the meniscus, the bottom of the meniscus, up to the 1 liter mark, all right? So as stated here, we dissolve in water. As you said before, we don't add water all the way up to the top initially. We just add enough water so that we can effectively dissolve the potassium permanganate, and then we add more water until the meniscus gets up to the 1 liter mark. And then in practice, what we do is stopper it after that and shake it up again, and we would have successfully made the solution of this molarity. All right, so that's basically how this is done. Okay, so I'm going to stop here. The next video, I'm going to go through these examples, and these are typical examples of problems involving molarity. All right, so until next time.